And in this particular example, what we find is you have an instantaneous source at the center, and this could be recreated in the lab by just taking a drop of dye and releasing it into a solution. And then what you'll see over time is that dye is going to spread out, right? So if I had a way of measuring concentration, so one of the techniques that you can easily use is some kind of spectroscopy that's correlated with how much concentration you have. So if you use any of the spectroscopic techniques, you can not only find concentration at the center, but how it distributes over. And that distribution arrays are pretty good when it comes to looking at color. So you can see the color density is going to get spread out, and the zinc is spreading out. And so that problem involved thinking about a similarity solution where you not only have to scale the x-axis, but you also have to scale concentration. So there are a few important ideas that come out of this particular analysis and this particular equation. And those ideas are related to viscous transport phenomena, as well as things that you probably will learn in thermodynamics class and elsewhere. So this concentration distribution, right? So if I look at this concentration distribution, we said this resembles the normal or Gaussian probability distribution. And in this probability distribution, you have peak centered at x equal to 0, and your variance is so one thing you can do is, if I go back and look at my partial differential equation, the fixed second law, you can check that this satisfies it. Okay, so other thing that you can figure out from here is, I have the concentration, I can also figure out the maximum concentration. So if you remember the notation from last time, Cm was our maximum concentration, and we had figured out from order of magnitude analysis that it should have a form where Cm is going to be proportional to e raised to the power minus I. Right? So that was from order of magnitude analysis. And if you look back in your notes, what you find is that the exact answer differs from the order of magnitude estimate by 1 over square root of pi. So that's pretty reasonable. So this is the power of order of magnitude estimates and scaling analysis is something that we want to really master through this course. So if you are going to work with similarity variables and you're interested in learning more about these, there are two books. There's one called Scaling by Barenblatt, which I have not managed to go through myself. I'm still working through it. And the other one is a more recent one on singularities, and that's again related to, written by mathematician Eggers, who's done a lot of work on pinch-off dynamics and how drops form from during jetting, during dripping, and so again, lots of beautiful math, but again, these are mathematicians writing for mathematicians. There are lots of fluid mechanics examples. For most part, you don't need many of the things there unless you work on fluid mechanics and similar problems. All right, so once I have this particular solution that we just derived, which is a solution for how concentration distribution changes over time, and spatially when you have an instantaneous point source or line source, I can use this to now rederive my error function solution in a slightly different way. So if I have initial spatial concentration distribution, so instead of getting a line source, I somehow managed to have on one side the concentration is high and it's C naught, and it's an extended source. This is your concentration, and we need to figure out how this. So it could be I take a sponge with dye in it and dip it into solution, and then that's an extended source, and now dye is going to come out of it. So you know when dye starts to come out of this extended source, if I consider a differential element, and this differential element is some distance zeta or away from your origin, and it has some mass dm, which is given by concentration times area times this width. Okay. So the governing equation remains the same. So that essentially means we are still neglecting any reaction terms and so on. And we assume homogeneous distribution with concentration defined at initial time as C naught if x is less than 0, 0 if x is greater than 0. Okay, that's just whatever we sketched, we are just writing that mathematically down. So for the differential element, dm at point this distance away, you have, as we just wrote down, a zeta, which of course you can remind yourself that this is just the area is some area, so x and y and z. So this is the x-axis and the other two are y and z. So for time greater than 0, the concentration at any point x is due to, so if you want to figure out the concentration at any point x due to diffusion from dm element, then we know from previous example or derivation, we get this concentration is going to be m naught, and m naught was mass per unit area, so here it's going to be dm over a, square root of 4 dt, exponential of minus, and that's your total distance over 4 dt. So this is the concentration originating from one differential element. If I have to figure out the total concentration there, I have to sum over all the differential elements. So if I sum over all the differential elements, we use the so-called superposition principle. So we superpose all the solutions, or we just integrate over everything that is contributing to this concentration, and that is going to be minus infinity to 0. Now I'm replacing dm by c naught a zeta, and then this is 4 pi dt exponential of minus x minus this over 4t, and then there's of course square. So if you look at this carefully, it starts to looks somewhat like the error function solution, but there are a few steps more. And I think to make life easier for you, let's do all those steps in some detail. So to compute the integral, we make a change of variables. So our goal would be in next 2 or 3 lectures, go through all the basics, and then they will have 2 recitations. One this week, later this week, and the other one on next Tuesday, because I won't be here. So I'll have Phil solve a few problems for you where you'll be able to see examples of all kinds of differential equations, but applied to heat and mass transfer problems. Yes?
What's the difference between those 2 letters?
One has one.
Like what letters are they?
I think this should be called zeta. And I don't remember what this is all Greek to me. So yeah, so that is definitely zeta, and this would be psi. So once we do this change of variables, then we can rewrite our concentration in these new terms. So I can get the C naught over root pi outside, and then we get infinity to x over 4 dt minus exponential of minus zeta. So this is zeta, and then to get the upper bound on the integral, we set psi equals to 0 in the definition of zeta. And what this means we have here is concentration variation is going to be, because of minus sign now, I can change these to from x over 4 dt to infinity, and there's one more step here, which is to recognize that I can write my integral as something from 0 to infinity exponential of minus zeta squared d zeta minus 0 to similarity variable, combined variable, exponential of so this particular integral is so when you do analytical methods in research or on a daily basis, in old days we used to have a book of table, a table of integrals, and then you would just go and look at those and see if this has some name or solution. From table of integrals, you can say this is pi over 2. These days you can just Google it or go to Wolfram Alpha. And the other one is called error function, where error of v is just 2 over root pi 0 to pi exponential of zeta squared d zeta. And the other way to write this would be from 0 to whatever pi, and then divided by 0 to infinity exponential of this. So this implies your Cxt is C naught over 2, 1 minus error function, and of course you can also write that as error C. So if I were to look at the concentration
over time, you'll start seeing that it changes the following way.
So one of the things we'll talk about later is if I had inserted this dye in a fluid moving with a constant velocity, right? The dye and will be advected at that velocity because the fluid is moving, but this diffusion will continue. So we'll need to later figure out how to distinguish the flux that is due to flow and flux that is due to just diffusion. So we'll get to that maybe in 15-20 minutes, but this is a good opportunity to remind ourselves that one of the things that's driving all this diffusion is, at a molecular level, is known as Brownian motion. And Brownian motion was discovered almost 200 years ago, and people would spend time looking under a microscope. The distinction between everyone else who looked at it and Robert Brown was that he was probably the first guy to go through the whole range of particle types and sizes and figured out that if you have small enough particles dispersed in a solution, they are going to go and do this kind of random motion. And that random motion now we understand is there because every molecule is doing this kind of random motion. How fast it jiggles really depends on kd forces. So if you increase the temperature, it moves faster and faster. And when you take a particle that is of a micron size, then that particle is small enough that all these random collisions with all the molecules around it are able to move it. So it's like having a really small piston that gets affected by collision of all the small molecules. So when you think about macroscopic pressure, the reason why you have macroscopic pressure is because there are hundreds and thousands and billions of molecules hitting the wall all the time. And here, the same pressure that arises from all these random collisions gives rise to Brownian motion. So Brownian motion is fundamental to understanding of soft materials, and those of you who work in soft matter will probably spend a lot of time thinking about it. The question that we need to address here is, so at a molecular level you have all these molecules doing their random walk, but at the macroscopic level you still see the concentration changes in a well-defined way. So the equation that we were solving earlier is a deterministic equation. So this is a deterministic equation, so Fick's second law. That's a deterministic equation. So how do you get a deterministic equation and a well-defined trajectory even though you start with a random walk? And so one of the questions that we ask here is, what is the probability of finding a particle or a molecule at a position R after some time, after time t, if molecule takes a random walk. So random walk means it's a walk without memory of where it has been before, such that each randomly directed jump, I'm just writing everything, but is of length L and requires time tau.
All right, so that's the question. So if you had a random walker where each step is of the same size and each successive step, just depends on where you were in the previous step, and you have probability of going in any which direction. And if it's in 3 dimension, you can have 3-dimensional probability. You can step in any which direction, but you don't remember what you did 5 steps ago. So this is the reason why this is also compared to a drunkard walk. Right? So that's drunkard walk statistics or random walk statistics. So if I were to define my position at time t as r, and so this position vector r is at time t, and then some time interval, a time interval tau before it, it's at the previous step, and so this distance is going to be, since my jumps are all of the same length, this r should have the magnitude of L. Then I keep going. So even if my drawing doesn't show it, you have to assume all the steps are of the same size. So this is also size that. So we are going to define a probability density, PRT, multiplied with dr. So this is probability density. When we multiply it with dr, we get the probability, and dr is differential range of positions. And I think to be notationally consistent, I should just put So that's our probability. R is a vector of length L with random direction. So if I have to get to R, I need to worry about 2 things. One, I have to be 1 step away from R. At 1 time step away. Right? So I should be at R minus R at T minus tau. And then which is going to have, and probability of that happening is P of R minus R, T minus tau. And then the other thing I need to do is have a successful jump to new position. So in reality, you can have a distribution of jump sizes, and you might have a distribution of time scales over which you make that jump. But the simplest case is when we assume all step sizes are of the same length and require same amount of time. So once we have these 2 things available to us, we can write the overall probability of landing at position R at time t, and that's going to be related to. So we are not going to do much with this kind of probability calculation. I'm including it here so that we have some notion of how people who do molecular dynamics think about these things, and how some of the microscopic or molecular picture connects to all the macroscopic things we'll do in this course. Yes?
What is that you have next to the capital R?
Let me write it more cleanly. It's capital lambda.
Okay.
So that's the successful jump probability, and this is defined to be equal to R magnitude of R minus L over 4 pi L squared, where you're using the definition of Dirac delta function, and this function is defined in such a way that if you have x minus x naught, then this is always going to be 0 for all x that are not equal to x naught. And if I take the integral, when it's multiplied with a function fx, then you get fx naught. Again, we're talking about this just for completeness, so don't worry about this in context of solving any homework problems or anything. So this is sort of the integral that arises in context of calculating probabilities of being somewhere, whether it's trying to model an animal who's foraging for food, a mosquito that's flying, searching for victims, or you are trying to look at polymer chains in solution, as well as colloidal hydrodynamics. And that equation is called a Markov integral equation. Again, saying that for completeness. So here my probability distribution of making that jump is normalized. So for a random walk, if I look at the average then this average value of single step displacement vector is equal to 0. So again, if I think very simply, then this is some kind of an ensemble average of a very, very large number of steps. So if I think in one dimension, the probability is that you can have a positive step or a negative step. And if you take large enough steps randomly, it's like flipping the coin, heads and tails. Randomly, the average should come out to 0. There's equal probability of taking a left step and a right step. So that's why this is 0. But what is non-zero is the second order term, and or if you take mean square, check it also right as R times R. So this is going to be, that's actually the magnitude. I shouldn't really write like that, but this is a dyad. We'll talk about dyads more, but it's two vectors multiplied together. So when we do that and calculate this, this will give us a value. So again, the key idea is the mean square value of this is proportional, is something you can evaluate. So that's a single step. We would want to do n number of steps, a large number of steps. So it turns out that this whole probability equation can be written as a Taylor series, and if you do some rearrangement, in the end, it is possible to derive an equation that looks like this. So now we have an equation for probability of finding a particle some distance away, and this equation is from molecular perspective, and it involves randomness, so it's a stochastic equation. So this stochastic equation is the governing equation for determining probability density.
Is that a P? Partial P, partial?
So both of them are P. Probability. So that's your equation. So this is a probability equation. If you compare this with your diffusion equation, which is macroscopic, which actually was established even before people believed they were molecules, and this is deterministic viewpoint. They both will be equivalent if we can figure out how to correlate concentration and probability and diffusion coefficient and the prefactors. So let's call this A, let's call this B. So while A governs the probability density of each one of n molecules, the overall distribution of solute molecules is of course the sum total of all these probabilities. At any instant, can be described as sum of all probabilities, such probabilities. So you can write C of T to be sum of all these probabilities over whatever you want, Avogadro's number of molecules or n number of molecules. And if that is possible, then what you get is L square over 6 tau is equivalent to D. So if I rewrite everything in spherical coordinates, then dP over dt is d over r square dP over dr. And something that you'll become familiar with over the course of the semester is whenever you are looking at these derivatives, it's r squared for spherical, it's r raised to power 1, r raised to power 1 for cylindrical, it's r raised to power 0, r raised to power 0 for Cartesian, right? So all three, whenever you see r squared and r, whenever you have spherical, it's going to have these this form, and that leads to some interesting. When you start solving enough problems, you'll see that if I had, say, this equals to 0, then my constant would be equal to this, and whenever I will integrate to find P, I will have C over R squared. Likewise, you can notice if you had D over R for cylindrical and R here for cylindrical, then when you integrate, you'll always have dP over dr into R as a constant, and so on. So those kind of ideas you hopefully get used to. But here, this is something which we solved in context of one-dimensional case. So the probability in 3 dimensions is going to be multiplication of whatever we get in one dimension into the second direction, into the third direction. So when you multiply it 3 times, you get 8, and you get 3 over 2 instead of 1 over 2. And in the exponential, it's minus x squared plus y squared plus z squared. So altogether, it's r squared. So this is the probability of finding a particle at position R after time t. And this probability is correlated with what you determine from concentration map. And so that shows you the equivalence between these two. And to get that equivalence, we also use the idea that a diffusion constant is some mean square displacement over a time step, over a time scale. So these ideas are quite interesting because one, it also describes how far. Now the reason why I keep repeating mosquito flies is not because I'm from India, but it's because in 1905 somebody posed this question in Nature, and Lord Rayleigh responded by saying, I calculated that a while ago. It's this distribution. So that's the answer to this distribution. And so it was used, calculated by Lord Rayleigh in some other context, but a lot of early work on writing the stochastic equation and other version, which is called Langevin equation, was done in between 1904 to 1920 by Einstein, Smoluchowski, and Langevin. Okay, so this is what we get. The other thing that is probably going to interest some of you, or probably already does, is if I want to think about polymer chains in solution. Then polymer chains in solution are often drawn like this by physicists at least. We don't care about the chemical details of the thing. But its shape is said to resemble that of a random walk. And if I can say that, then that allows me to describe polymer chain statistics. And immediately I can write the mean square size of this chain is going to be somewhat similar to that formula of contrast with so you're taking n steps, so you're taking n step each of size. So this has the same form in the sense that mean square displacement is proportional to number of steps. There, the mean distance you travel, mean square displacement that you have from diffusion is proportional to time. So if I write it, turns out, again, the mean displacement, if I were to try to find mean displacement, that's equal to 0. Mean square displacement is let's just look at the magnitudes, is equal to a well-defined quantity, because this turns out to be so this gives you r squared is 6 dt. So if I wanted a displacement, measure of a displacement, I'll take square root of this. And if I take square root of this, then I'll get this idea back that the distance, representative distance traveled by diffusion is root b. So if I have two ways of going from here to there, one of them is diffusion, the other one is convection, which involves just sort of floating with the flow, going with the flow. So if I go with the flow, then I have a certain velocity v. So if I have a certain velocity v, what is going to be the displacement in time t? So I have a velocity v and this thing is moving, an object is moving with velocity v. What is the distance traveled in time t?
VT times.
Vt, right? So that's linear in time. So whenever you're going with the flow, the displacement is linear in time. Whenever you're going diffusively, it's square root with time. So of course you'll get much further with convection, with convective effects. So in reality, at least when you're thinking about big reactors, it is useful to remember that most of the mixing is driven more or less by that convective term. But locally, you still always, whenever there's going to be a concentration gradient, there's going to be diffusion, and diffusion plays significant role in all sorts of processes, especially in small scales where convective effects cannot be that large. All right, lastly, so this is just a foray into molecular picture, but one of the other important things Einstein showed in his 1905 paper that I've already posted online for some of you who are curious about it to read and see, is this idea that if you define zeta as a friction coefficient, U as mobility, which is of course 1 over friction coefficient, kBt is your thermal driving energy or force. So it's units of energy, so let's call it energy. Kb is the Boltzmann constant. So what Einstein argued was the diffusion coefficient is more or less controlled by the driving force, and this friction coefficient is a resistance. So this resistance for a sphere can be written using Stokes' formula. For a sphere. So if you write it for a spherical particle, then that's just 6 by viscosity and radius of a particle. So if I'm looking at liquids and a diffusing particle in those liquids, I can find diffusion coefficient. If I equate A with the molecular size, then I can find the diffusion coefficient for within that liquid. And so if I use this formula, then what we get is Stokes-Einstein equation. Now Stokes-Einstein equation is something I would want you to familiarize yourself with, where diffusion coefficient of A in B depends on phi, viscosity of B. So with Stokes-Einstein, I can always get, if you want the simplest estimate for diffusion coefficient for a protein in solution, then that's what you use. If you want a estimate of diffusion coefficient for a polymer chain, this is what you use. So once Einstein came up with these two ideas, then because Kb times Avogadro's number is gas constant, so it became clear that if somebody does an experiment where they can track a particle around over a certain period of time t, and then take the statistical average, so basically plot mean square displacement as a function of time, from that slope you could get d. And then in his paper he mentions that if somebody makes this calculation, they'll be able to verify and find the value of Avogadro's number. And Perrin did that in 1908, and then that's also described in some of the papers I added. So those in your folder, you'll always find some papers that are, I guess I'm going to label them for extra papers for extra curious people. So if you want to read them. But there will be others that I'll say are integral to this class. So some of these historical things, papers that I added, you might not want to spend time on unless you're really interested. So with this background, what we've done so far is I essentially wanted to delay this discussion of conservation principles and solving standard steady state problems in heat and mass transfer till we got introduced to vectors and scalars again. But what we've done so far is we've got insight into 2 or 3 things. One of them is the molecular diffusion, which essentially involves random walk of these millions of molecules. If you look at the probability distribution of those molecules over time, it will give you the same kind of answer that you get by solving fixed second law. The second thing we've looked at is how do you do an order of magnitude estimate? So we're going to do that again and again. Third thing we looked at is an example of how do you solve similarity, how you solve PDEs, and for solving PDEs we used similarity variable approach. And now we'll go back and revisit some of the things we defined in the first lecture, and then from Friday onwards you'll be able to solve all kinds of heat and mass transfer problems, hopefully. Okay. So among different things you revisited on Friday was the definition of scalars and vectors. So temperature, concentration, charge, these are all quantities that require you to know magnitude of it. Right? So they are all scalars. Even though they are scalars, they can vary spatially and temporally, which means you can have, for example, temperature vary with position as well as time. Then if I think about quantities like velocity, v, momentum per unit volume, rho v, sum of the fluxes, they are all vectors, and you need both magnitude and direction. Okay. So if I go back and think about heat flux, we said heat flux arises because of gradient in temperature or temperature variation. So temperature is a scalar. Temperature variation is giving rise to heat flux, which is supposed to be a vector. So then we need to figure out how to convert that scalar into a vector. And of course, when I'm thinking about heat flux and I use index notation, I should remember that I can write it in component form where you have 3 numbers, Q1, Q2, Q3, and 3 unit direction vectors, E1, E2, E3. And if it was X, Y, Z, then of course you replace this with QX, QY, QZ, and this would be, say, I, J, K. You can use all sorts of different notations. So if you go to different books, they'll use slightly different notation, and luckily for you, you're taking only one transport phenomena class. I made a mistake of taking 2 different fluid mechanics class in the same semester, and they both followed very different notation. So somehow I survived that. But yeah, every time you read a new book, new paper, they'll have slightly different notation. All right, so now what I want to figure out is if we have a scalar function temperature, for example temperature, that varies in space with position, and we can do this in any coordinate system we want. Let's do it in Cartesian because that's easy to see. The rate of variation is different in each direction. So dt over dx, dt over dy, dt over dz is different for each direction. So since it's different for each direction, we want to figure out how temperature variation is creating this heat flux. So we need to define something that allows us to look at both the magnitude and the direction, and that's where we use the use of gradient operator allows us to determine both direction and magnitude of flux. And again, if I had a function phi, then this can be defined as EI phi comma j, where this is comma denotes differentiation with respect to j. So there are two things that you want to convince yourself. One of them is, you may or may not like comma notation. You may or may not use it for too many problems in this course and other courses that you're taking right now. But all of you are now graduate students, and many of you are probably going to work in areas where they'll continuously use this comma notation. Especially if you work in areas like mechanics and rheology, then that is going to be very useful in future. So this is an opportunity for you to also learn some things that will allow you to read papers in your field if you go into those fields where they use these, but otherwise talk to people who use this notation and make progress from those collaborations. So if I write this in this comma notation, of course I could have written it in full glory detailed form. And when you write it in full glory form, you realize that if you have to do hundreds of these derivations, which is what Einstein was trying to do, it's going to tire you out pretty quickly. So to save yourself some effort and time, or save himself some effort and time, he introduced this index notation and summation convention and the comma notation and so on. So because now I have both direction and magnitude, it makes sense that in Fourier's law, I have flux, which is a vector, being calculated from temperature, which is a scalar. But then the question arises, if I'm thinking of gradient of a scalar, what is its physical meaning? And what direction does it point to? Okay, to really do that, we need to find a relation between the gradient and direction of the variable. This wasn't discussed on Friday, right?
No, I didn't discuss this.
Right, so we want to make sure that when we are using this gradient, and we are going to use this in heat transfer, mass transfer, everywhere, we at least understand its physical meaning, and we understand that it points in the direction. So we know that when you bring a hot object and a cold object in contact, the heat transfer always takes place from hot object to cold object. So we have to make sure that that direction is right, and we have to make sure that the absolute value of this gives you the right magnitude and as well. Right? So if I consider a small displacement, infinitesimally small displacement vector dr, where the magnitude of this vector is ds. Then the unit tangent vector in the direction of dr is, say, t, and if you want to find unit vector in direction of a vector, we just do this, where we take the vector divided by its own magnitude, which in this case we said is equal to ds. So far we've just used the standard definition of a displacement vector and defined a tangent vector that points in the direction of that displacement vector by, again, using the standard definition of vectors. Now, the rate of change of a scalar phi in the direction of this tangent vector is given by dot product between the gradient and this t. So if I use the index notation again, I can do this multiplication, and when I have this multiplication done, I get ti d phi dxi, and I can write this in expanded form. So if you always want to write expanded forms, then there's no value in writing the index notation, but we're trying to give you time to become familiar with both the notations. So now if I have t dotted v phi, because my t1 is, so t is defined in this way, right? So dr has three components: dx, dy, dz, or dx1, dx2, dx3. All of them will appear now. So I end up with t1 will be dx1 ds d phi over dx1 plus dx2 ds is t2 multiplied with the second term, and then dx3 ds d phi over dx3, which all the x1s, x1, x2, x2 terms cancel out, and what you're left with is d phi over ds, which is your directional derivative of phi in t direction. So now consider a surface phi x is equal to constant. So I can think of maybe a surface that has the same temperature, and away from this surface the value is different. So this could be an extended area with the same value of the scalar. So because phi is constant, your dot product of t and gradient of phi is going to be equal to 0 for displacement along this surface. Right, so if I go along this surface and take directional derivative of phi in that direction, tangent direction, then that's going to be equal to 0. So that's what we write here. And what this implies, as t is tangent vector to the surface, it follows that t is perpendicular to gradient in phi. That is, gradient in phi is a vector perpendicular to the surface of phi equals to constant. So gradient of phi is vector normal to the surface with phi equals to constant. So this is a very detailed mathematical way of saying that the gradient in phi is always going to point away from constant value of temperature to the next value of temperature where it's varying. So it's written in this fashion because when I start to understand what that symbol means, then all this meaning that we assign to it is clear with just this much. So it allows you to summarize things to. In old days, people would write. If you write books without using these symbols, then you'll always need to go through that whole paragraph of description that this is the direction in which this points to, this is the magnitude that you have for flux. But once I understand this notation, every time from now to forever, whenever I'll use gradient, you'll immediately see in your head. It has 3 components. This is the magnitude of these 3 components. This is the direction in which it points to. And because this always points in the direction, it always points in the direction of increasing value. So, and the mass transfer or heat transfer always goes from higher temperature to lower temperature. That's why we use a negative sign. So for an arbitrary orientation, the flux normal to a surface, so this surface could be my table, could be an object. So if I'm trying to figure out flux normal to one of the directions, one of the planes here, then that flux is given by n dot q, and of course this would be n dot gradient in t. So if n is parallel to y-axis, then you can use this to find qy, and that is just k dt. So in next few minutes, we'll look at another idea that is important. So this is again definition, and probably is I'm repeating few things from last week, and of course for people who've taken transport, this is these are things you should be familiar with. So you have molecular or diffusive flux, which we define using Fick's first law, right? So that's Fick's first law, and again you have gradient, and now as soon as I see gradient, I understand it has 3 components, so you can allow you to define things in 3 dimensions. But in reality, you are interested in mass transfer. The mass transfer takes place both by and by convective means, which is due to bulk flow. So to find out how much of the species flux is contributed by diffusion, you have to first think about how to define it with respect to a moving frame of reference and a stationary frame of reference. And that means you can choose between a whole, I think 4 or 5 at least definitions. So it depends on the definition of mixture velocity. So we'll write these definitions in a few seconds. So if I am looking with respect to fixed coordinates, then molar flux, number of moles of species I with respect to fixed coordinates is given by Ni, and that is related to the mass flux, mass per unit area per unit time, by this formula where Mi is molecular weight of I. Because when I divide, for a species I, when I divide the mass flux per molecular weight, it gives me number of moles per unit area per unit time. So this total flux is such that it accounts for concentration of I species and velocity of I species. In fact, you can define velocity, so relative to fixed origin, you can define velocity of species I by Vi is equal to Ni divided by Ci, or small ni divided by rho I. So these are two concentration in molar and mass units. So remember, if I look at all different molecules of species I, and I take an average of all their velocities, and they're doing this Brownian motion in all sorts of directions, then this is the average velocity. So on an average, they might be moving in one direction. And then if I look at my whole fluid, it's going to have some velocity v, which is going to be an average of all the velocities contributed by all different species. So I could have a binary mixture, then it's just VA and VB, where A is the average velocity of all A molecules, VB is the average velocity of all VB molecules, and then depending upon whether I use concentration units or mass units, I end up with different average velocities. So we use two reference frames, two useful reference frames in mixtures R, and you can look at the discussion both in Dean and in BSL for this. Mass average velocity, which is V obtained from averaging over all individual VIs, and then there's the molar average velocity, which is whenever we write anything defined with respect to molar average velocity, we are going to use subscript m. And for most part, after today, we'll stick to mass average velocity, but again, for completeness, we always introduce these things. Where omega I is rho I over rho, mass fraction, and xi is ci over c, which is mole fraction. So many choices exist for defining flux. So capital JI is molar flux with respect to mass average velocity. JIM, capital JIM is molar flux with respect to molar average velocity. Small ji, which we use quite often, is mass flux with respect to mass average velocity. And for the fun of it, you can look at how these things transform from one to the other based on their definitions of velocities and reference frames. But the idea is that my total flux, which I said is CIVI, is going to be contributed by two terms. This one is a convective term, this one is a diffusive term. So I can have diffusion even if velocity is zero, right? But if I look at this a little more carefully, what we are also implying here is my diffusive flux takes into account right, so this is if I had my ink inserted into a flowing liquid, then my ink is still going to diffuse away from where I inserted it. But that center is itself moving with a certain velocity, that's the velocity of bulk fluid. So the diffusive flux is going to be defined with respect to, in a reference frame that takes into account the overall mixture velocity. And with that definition, if I take sum of all the molar fluxes, you give me CVM. However, if I look at all the diffusive components, it's going to give me 0. You can prove these identities to yourself, and I can also write Ni in terms of Ci Vm plus Jim. Likewise, you can write Ni is equal to rho Iv plus Ji convective, diffusive, could have been in the reference frame of molar quantities, molar velocities, and here again Ni is rho V, whereas sum over all the diffusive ones. So by definition, molar fluxes relative to molar average velocity sum to 0, and mass fluxes relative to mass average velocity sum to 0. All right, so this was essentially needed to remind us that in both heat transfer, mass transfer, and later in charge and momentum transfer, there's always going to be a molecular term or a diffusive term, and the other contribution is because of flow. So some amount of concentration can always be brought about with a flow, and then the other thing that you already know from the discussion earlier today is, because if you're bringing something with a constant velocity, the distance you can travel is linear in time. If you're bringing it diffusively, it's root t in time. So convection is always more useful in mixing things, or can mix things faster. And that's something you explore every time you stir your coffee. So what we are going to discuss next time, and just say a few things about this time, is the journal form of conservation equations. So once we need 3 ingredients. We need constitutive relationships, we need conservation equations, and then we need an understanding of what happens at interfaces, what happens at boundaries to solve any problem in transport phenomena. So when we'll write a general form of conservation equation, the idea is that it's going to be a balance between rates of accumulation rates of transport. So transport can be by convective as well as molecular fluxes, and rates of formation. So rates of formation in, say, context of mass transfer could be a chemical reaction that's creating a species. So if a chemical reaction creates a species, then you're going to have more. The key thing about conservation equations is they are derived from first principles, and have universal form. It does not matter what kind of fluid you're looking at, what kind of material you're looking at, you'll have the same conservation equation. In contrast to constitutive equations, which are more or less empirical. They're based on experimental observations, and they are material dependent. You can have Newtonian fluids and non-Newtonian fluids, for example. So to really work in this with constitutive equations, what we often do in the undergraduate classes is we start by looking at rate of accumulation, rate of transport, rate of formation within a control volume. and you can write each one of these terms independently and then write this detailed sum that eventually converts into a differential equation. And then we learn how to solve those differential equations. In the graduate class, what we are going to do is we are going to derive the general conservation principle, and instead of drawing control volume every time and trying to do this balance, we'll say this conservation equation applies, and then start from there. So the shell balance method that's is used for introducing this to undergraduates is great for one-dimensional problems and some problems. What we will do can be applied more generally, and of course helps you to solve even all the shell balance type problems that are there in BSL, for example. So if you're trying to look at some background material from BSL or Revisited, then many of the problems there are done with shell balance approach, but we will, for most part, start with conservation equation. So the conservation laws are derived using control volume, and this is nothing but it's an imaginary closed region in space selected for its analytical convenience. So what we'll see next time is how to think of a control volume, figure out how much energy is coming in, how much energy is leaving, and how much is being accumulated, and how that leads to increase in temperature. Likewise, how much mass is coming in, how much mass is leaving, if there's any reaction that can add to or reduce the amount of material, and then determine how much is accumulating. And the general conservation equation will then allow us to write fluxes and balances for also charge systems and fluid mechanics later. All right, we start from here.